Morning, Physics 30. I hope you guys are all doing well today. Welcome to your lesson about diffraction and interference. I discovered a cool thing like 2 seconds ago. I figured out how to get rid of that top bar on the web browser. Yeah, I know. It's a sad victory, but that's okay. We're working on my tech skills. I'm just impressed I haven't busted anything yet. Okay. So, ladies and gentlemen, for our lesson on interference and diffraction, this is another really tough topic. So if you'll notice on Google Classroom, I have a grand total of 5 more videos for the Khan Academy for you. 4 of them I recommend that you watch for sure. One of them is, if you find this cool and want to learn more about it, watch that video. So, like we did with lenses and mirrors, I'll be referring back to when's a good time to pause this video and then jump over and watch those Khan Academy videos to kind of broaden your understanding of these topics. All right, so ladies and gentlemen, let us begin. Okay, so we're also going to be drawing on some of our knowledge from last year with waves. And I'm pretty sure, hopefully, you guys remember what interference is. Okay. And diffraction is another property of light. So it's the bending of light as it moves around a corner. So we are going to be focusing on Young's double-slit experiment and diffraction gratings, which work very, very similarly. Okay. So a scientist named Mr. Young, he predicted that if you shone monochromatic, now remember the Latin, mono in Latin means one, chromatic in Latin, color. So a light of one color or a light of one wavelength is going to go through 2 narrow slits. Now we're talking like super narrow slits. He would expect to see just 2 bands as the light scoots through these and goes to the other side. However, that's not what he saw. He did not see this. He did not see light forming 2 slits. Okay. What he did see is that when you shine a light through it, shine monochromatic light through these 2 slits, you wind up with a many, many bright bands of light. So he had to come up with a reason for this. So it has become what is known as Young's double-slit experiment. And this is huge, huge evidence for the light as a wave theory. So remember, we're doing like light is a wave for chapter 1, light is a particle for chapter 2. Because light can be both. Okay. All right. So we're going to scroll down here. So to explain the results that Young saw, the many, many bright lights, he concluded that light has the ability to both diffract and interfere. So these are things that we talked about last year when we looked at waves, mechanical waves. So we looked at the ability of water waves to bend as they kind of go around a corner. And we talked about how sound waves are going to interfere. So just a bit of an aside. So you guys know those like really, really fancy noise canceling headphones that you get? And when you put them on, they like cancel out all sound. Well, they actually use the principles of interference. So when you have a sound wave that is coming into your fancy noise canceling headphones, there's your sound wave. Well, guess what? These fancy headphones, I can't even think of a brand. I don't know, like, do Beats do noise canceling headphones? I don't know. I still use the like really, really cheap headphones that come with the iPhone. My iPhone's like 5 years old, so my headphones are 5+ years old. Yeah. I have a set from a previous iPhone too. So they're ancient. So if this is your wave that's coming into your fancy, we'll pretend that Beats do noise canceling headphones. So coming towards your fancy Beats headphones, well, the noise canceling headphones are going to send a wave back towards this. Well, remember what you have with your sound waves, where these 2 waves come up across each other? Well, if the waves are opposite to each other on that sound wave, you're going to wind up with a flat line. You're going to wind up with no sound because the waves cancel each other out. So that is how noise canceling headphones work. Isn't that sweet? I think it's pretty sweet. Okay, so that is interference. So that's what we talked about it with sound waves last year. Now, if light can interfere like this, then, well, guess what? This hugely supports the light as a wave theory. Okay, so there you go. Hey, we even have it in the notes. It's strong support of EMR. Now, diffraction, ladies and gentlemen, it's how a wave spreads out as it's going to pass through an opening. Last year, we talked about if this slit was like a gap in a wall or some rocks, and these were ocean waves, the ocean waves are going to curve like that. They're going to bend as they go through that gap. Well, light does this too. So these lines are going to represent a part of the wave. So we're going to say that the crest or the top of the wave. So if this was a light wave, then that bit there would represent these lines, and the gap in between them would represent the troughs in your wave. Okay, so in light's double-slit experiment, what happened is light is going to pass through two slits, and the light is going to bend around these openings. So if we, on the next page, we've got a diagram where we'll draw more about what's happening with this. So, and as they bend, and if you have another light wave here, notice you're going to have interference. The waves are going to start overlapping with each other. And when light waves overlap, well, you get this, noise canceling headphone effect, I guess we could call it, or interference. Okay, so I've got some more diagrams down here where we'll look a little bit more at interference. So you're going to wind up with bright spots and dark spots. Okay, so we'll talk about more about that down here. Okay, so that is why we get the many, many slits. Oh, and the top of the bar is back. There we go. Okay, cool beans? All right, it's pretty cool how light and water and sound waves all behave similarly. Oh, I think it's cool. That's a pen. That's not the mouse. There's the mouse. There we go. Okay. So I went too far. There we go. So back down to our diagrams where we're talking about interference. So with your fancy Beats headphones, what your Beats headphone or your sound canceling headphones are doing is what is called destructive interference. So that's where you're going to cancel out your wave. Okay. So as opposed to not hearing sound, you're not seeing light. Okay. So when the waves are going to bend and overlap with each other, if those light waves are going to bend, well, here we've got that one wave like we drew up here earlier going this way. And then along the same route, we have our blue wave going this way. We get nothing. Okay. And then as they continue to move, because wave moves, they're going to carry on their way, doing their thing. Doing what waves do, they are going to have this lovely nothing, okay, right when they overlap. That's going to be the dark spots on your diffraction grating or through your Young's double-slit experiment. Okay. Now, when we have bright spots, that's where we get constructive interference. So here we have, now notice we've got wave A here, and then we've got wave B here. Well, when they're going to collide, they're going to add to each other. Now, because they are red and blue, when they're going to add, we're going to wind up with wave purple. Okay, they add. That's the bright spots. Okay, and then the waves are going to continue on doing their wavy things. They're going to wave at each other as they go by. Yeah, you knew that one was coming. You knew that one had to happen. Okay. All right. So that is our constructive interference. So once again, I want you guys to pull out your highlighters. We're going to highlight constructive interference is where you see a bright band. And destructive interference is where you're going to see a dark band or a dark spot on the screen when you're shining your light through it. Okay. Any questions? We're not in class. Okay. If you have questions, make sure you sign up on Google Meet for video chat. Okay. All right. So that is a pen. I need the mouse. There's a mouse. All right. So, ladies and gentlemen, this is actually a really good time to pause this video, and a really good video to watch right now would actually be the YouTube video titled Diffraction Gratings. So it talks about diffraction gratings. That's a great one to watch first. All a diffraction grating is with Young's double-slit experiment, you just have lots and lots of slits. Okay, many little slits instead of just two. So they do a really, really good job of explaining why we wind up really seeing the dark slits and the light slits. Okay, they do a really good job of that. So I'd watch that video and then come back to this one. Now, I will give you guys a heads up that at first when you watch it, it's a little overwhelming and it's a little bit tricky. And the aha, I get it moment comes at approximately the 10-minute mark in the video. So give it time, be patient with it. But when they start drawing on the waves, exactly why you get destructive interference and where it happens, that's the click. That's the, oh my goodness, I get it moment. Okay, sounds good? Okay, so pause the video and then come back. We're back! I know, fastest costume change ever. So remember how earlier on in the video I said I haven't broken anything yet? Yeah, yesterday I broke the internet. So the first half of the video up till now I filmed yesterday, and I finished filming the whole video and it was amazing, and then it wouldn't download, and then it was fighting me, and it deleted half of it, and then the remaining bit I could only use part of the video because guess what? The sound and the video were so off. It was painfully confusing. So I broke the internet. It's official. We're going to try this again and just really hope that the video actually does its thing and uploads or downloads or whatever it's doing. Okay. So we're back. So ladies and gentlemen, what we're going to do is we are going to look at exactly how constructive interference and diffraction are going to be happening in a Young's double-slit experiment or a diffraction grating. So the principles are going to be the same between the two. The only difference in Young's double-slit experiment is, well, there's two slits or two holes in a barrier, and a diffraction grating, you've just got many slits. Okay. So as you already saw in the video, I'm hoping you guys just watched. If you haven't paused the video and haven't watched it, don't worry, I won't judge, I promise. All right, so ladies and gentlemen, let's spend a decent amount of time looking at this diagram and see what the heck is actually happening here. So what we have with Young's double-slit experiment is we've got this barrier here and with two gaps in it. Now these bars here, they represent the peak of a sound wave. So here is our lovely sound wave. This peak here represents that line there. And then when we have a trough down here in the wave, that would be that middle part there, that gap. Okay, so this is as if we were kind of looking down at the top of a wave. All right. So what we have here is our wave is going to come cruising along this way, and then it's going to hit this wall here. Well, our light wave is just going to be absorbed by the barrier on these sides. Okay? But a little bit is going to go through these gaps. Now remember what happens to waves when it goes through a gap. It's going to diffract or it's going to curve. If you want to know why it's going to curve through a curve like that when it goes through a gap, I recommend you guys watch the video called that I attached on Google Classroom called the single slit interference or single gap interference. I can't remember what it's called right now. I put it up yesterday. Found it yesterday. So check out that one, the single slit interference, and watch that one. That's 100% optional. I'm not going to make you watch it unless you want to. That one tells you kind of more why waves are going to diffract, which is kind of cool. All right. So as our wave is going to diffract, this little bit of the wave is going to go through here and it's going to diffract. It's going to bend. Now, this is a huge mess. So what I'm going to do is I'm going to do my best to clarify it up so that way you can kind of see what's happening. So I'm going to draw the one set of waves, the one set of wavelengths in red, and then we'll do the other in green so we can kind of see what's happening. So this wave is going to extend out that way, like that. And as the wave continues, we've got a wavelength that is going here. And then a wavelength that continues this way as it continues to scoot. And then the wave is going to continue out that way. And then we've got a wave that's going like that. Okay, so we have the peaks of all of our wavelengths here. So remember, each of these red lines is representing that part of the wave. Now I'm going to use green because I've already got blue lines here and I don't want it to get any more confusing. So I'm going to use green lines to represent this wave. So this wave here is cruising along this way. Part of it's going to be hit here and be absorbed. Some of it's going to be hit here and absorbed, but this little bit of the wave is going to go through here. It's going to bend as it comes through, and as it continues to scoot, it's going to go this way. Now notice as I'm drawing these green lines here, these green peaks. So, oops, that's not. No, green's just the other way. Green's up there. Let's get rid of that. That's not green. There we go. Back to green. So when we've got these green waves here, notice that they are overlapping with these red waves. Now remember what happens when waves overlap. They interfere with each other, okay? So we are absolutely going to be having interference as these waves scoot through there. Okay, so I know it's a bit of a mess. I know it's confusing, but we're doing the best we can here. Okay, so because these lines are already blue, I'm going to use blue. And what we're going to do is we're going to see where we're going to get constructive interference and what all of these lines mean. Okay, so we've got our screen with two slits. We've got your barrier with two slits. And then what we have here is an optical screen. So a screen that you're going to be projecting things onto. And this is just the front view. This is what you would see if you were looking at it from this perspective. Okay. So what's going to happen is, well, look where these, remember where we have these red and green lines, that's the peak. These lines are the peak. That's this part of a wave here. So well, look, they overlap at that point. Well, what's happening is if we've got this peak and this peak that are going to be lining up to each other, well, guess what? We get a much bigger wave. We get constructive interference. So anywhere where these peaks line up, that's where we get constructive interference. That's where we're going to get that wave to be bigger. Now, unlike sound waves, we're not going to get a louder sound when our light waves overlap, obviously. We're going to wind up with a brighter light. So here we go. Well, look at this. This is also where two peaks are going to overlap. Well, look, we've got two peaks overlapping here. And look, well, we got two troughs overlapping here. We got two troughs overlapping here. So as we continue, we can draw a line of where our constructive interference occurs. And then, hey, guess what? It lines up with this lovely bright spot on the screen here. That's supposed to be a straight line, guys. Let's try that again. Let's actually make this kind of straight. There we go. That's better. Okay, so we're going to get a bright line on the screen. Well, we get lots of constructive interference here, so we're going to get several bright lines. Well, look, we've got the peaks overlapping here, peaks overlapping here, peaks overlapping here, and peaks overlapping here. There we go. We got a whole other line of constructive interference, which is going to give us a nice, really bright spot on that screen. Well, look what we got here. We've got another, and this one's a lot easier. A nice straight line here. A nice straight line of constructive interference where the waves overlap there. Okay, so the same thing is happening anywhere where you get these red and green lines overlapping. You've got the peaks of those waves adding to each other, and you're going to get really nice bright spots, okay, on that screen. Now, this is why that this experiment was so instrumental in helping demonstrate that light behaves like a wave. So big evidence for the light is a wave theory, because waves interfere. Okay, so that's super cool. Okay, and waves diffract. So this is perfect evidence. Yeah, with experimental error, of course. So we got a nice straight line following all these different areas of constructive interference, and then we wind up with another bright spot. Now, we're going to talk a little bit about destructive interference and where these dark spots come from. Well, remember, destructive interference is where you have waves that don't line up with each other. So when we're going to be adding a wave like this, well, then you wind up with no wave as they're going to cancel each other out. So I'm going to use yellow here to show kind of where destructive interference is occurring. So notice here, well, I've got the peak of that red wave here lined up in where there's a white spot in between these green lines. Well, remember that gap represents a trough. So that's going to be destructive interference because we've got a peak and a trough lining up with each other. I'm going to make that yellow a little bit kind of more orangey. Maybe that might be a bit easier to see. Okay, so we'll then look over here. Well, here we've got the green peak and a red trough. And look at this, we got the peaks and the trough, peak and trough, peak and trough, and that is all lining up like that. So you get this row of destructive interference, which is then going to leave you with that dark spot. Okay, so all of these dark spots that you're going to see are a lineup of destructive interference, and you can find that at any one of those gaps. So you can see peak and trough, 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 all right, all the way through. And when you draw a line connecting that line of destructive interference, it lines up perfectly with that dark spot where you cannot see any bright spots of light. Okay. So that, ladies and gentlemen, is how Young's double-slit experiment works and the theory behind diffraction and interference. Now, I know this is really hard. I won't blame you if you guys go and rewatch this section of the video a few times. I would if I was you. Because when I was your age in high school, I struggled with this stuff hardcore. So don't feel bad if you're finding it tough, because it is hard. Okay. Alrighty. So watch that bit of theory a couple times, kind of see how diffraction and interference works. What we're going to do now is we're going to go look at our equations, and we're going to be coming back to this diagram and labeling what each of the letters means on those equations. So I'm going to select my mouse tool and I'm going to scroll down, and it's bringing down one of my red waves. That's upsetting. Well, I'll just erase the red wave. We will get over it. I'll get over it. Will you get over it? Hope so. Okay. So, the bright bands, ladies and gentlemen, are called maxima or antinodes. It's where constructive interference occurs. So highlight these in your notes. Okay? Put a star beside them and write on test. We don't have tests. They're not exactly on your test because we don't have tests. Okay? Just means it's important now, I guess. Habit. I can't get out of my being in the classroom ways. Okay. So the dark areas or sometimes they're called fringes. These are minima or nodals, and that's destructive interference. Okay, let's look at our equations. We've got two equations. One can be used all the time, and one can be used some of the time. Okay, so, and now that line's back. That's weird. Okay, to erase that. Okay, so lambda is our wavelength. Now this is the one you can only use sometimes. And we've got that later in the notes of when you can use it. But you can only use it when theta is less than 10 degrees. So we'll talk more about that later. And this one you can use in any diffraction grating or double-slit experiment. See if I can spell diffraction right. Okay. So you can use that in any of the diffraction scenarios you'll be given. This one you can only use if theta is less than 10. So we'll talk about that later. Okay, so lambda is your wavelength of your light or your EMR, and that will most of the time either be given to you in the question or it's going to be what you're going to be asked to calculate. D is the distance between the slits. So let's scoot back up to our diagram. And these red lines are really possessed. They keep jumping back and forth. Works, I guess. So when we're going to be talking about the letter D, so the distance between the slits, that's going to be this value here. So how far apart those slits are. So that distance there is going to be your numerical value of D. Okay, so the distance between those slits. Okay, back down. And that red line is back. I swear, it's possessed. Like I told you guys, I've broken the internet. Okay, so X is the distance from the center bright band to another bright band. Okay, so I'm going to scroll back up and we're going to talk about X. Okay, so X is the distance between the center bright band and another bright band. So I'm going to grab my pen again. This is the center. Okay, we'll talk about the value of n in a moment, but that's n equals 0. You can see it's that straight line. And the distance between that band and another bright band. So that is the value of X, that distance there. Now, one of the things in the videos that I will be recommending to you to watch shortly is they often talk about like X and 2X. So if we're going to go to our next bright band, which is here, well, the distance between this band here, from this here to here, that distance X, is going to be the same distance from here to here. So that's also X. So to go from the center to up here is going to be 2x, so twice the value of whatever this one distance is. So however, it doesn't matter when you're putting it into equation. If they say, oh, well, between band 2 and the center band and band number 2, it's this distance, just write it as x. That's completely fine. Because guess what? Our letter N takes that in part into consideration and deals with that mathematical issue. So don't worry about that bit. And N's the next piece we're going to look at. Well, we're already looking at the screen. We'll look at N. So N is essentially the number of the maxima or the order of maxima. On the video, I'm going to recommend they label it as M, but it doesn't matter. Okay, we use N, they use M, whatever. Okay, so N is the order of maxima. 0 is the center. Okay, 0 is your center node, and or antinode, excuse me. And then the second bright band off of that center, the first one off of that center here, these blue lines, that is going to be the order of 1. It's 1 band away from the center. Well, this one is N equals 2. It's 2 bands away from the center. Well, guess what, guys? Will you looky here? 2x, N equals 2. Well, when you look at your equation, well, you're dividing by N. So you have x on the top and N on the bottom. So you're going to be canceling out. If this is 2x, so twice as far from the first one, and that is 2, well, the 2's cancel. So ain't math grand? Oh, no. Math is grand. Okay. So that's the value of n. So your order number of the bright band. Now, when you're going to be doing your calculations, if it doesn't say otherwise, assume 1. Okay. So the order of number, we've already talked about that one up there in the diagram. All right, now L and theta. So we're going to talk about these together here. So L is the distance from the slit screen to the screen displaying the interference pattern. And theta is our angle from the center of the slits to a bright band. Okay, so let's go and draw this on our diagram. Grab that. Scoot, 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 scoot. Back up here. There. Okay, so I'm going to switch colors here, and I'm going to change to one of this orangey color. And we're going to be looking at theta and L. Well, L is the distance from here to here. Okay, well, right there. So the distance between the slit screen and the distance between the optical screen. So that is your value of L. Okay, so now L can be anywhere along here. It doesn't matter where you draw your L. So I'm going to choose, just for sake of ease, I'm going to make L right here down the middle. Okay, this orange band is going to be my L. Okay, well, theta is the length between, or the angle between this center line here and another bright band. Well, let's just use 1 because that's easiest. There we go. So there is where the bright band is. Okay, so look, I've made myself a triangle. That angle there, that is theta. So this angle here is my theta. So, well, look at this. I've got myself a beautiful right angle triangle now. And look at this. That's my length, and that is my x. So guess how I'm going to get theta? Tangent. Exactly. So we're going to talk about that a little bit later in the notes, but that is where this triangle comes from that we're going to be getting. The length of the screen, okay, and x, the distance between the points, and then that is going to be your theta. Okay, sounds good? All right, I know it's a mess. I know it's super busy. We're doing the best we can with what we got. Okay. All right, so those are our numerical values, and we have our possessed red line here. There we go. All right. So the distance between the slits, D. Now this may be indicated on a diffraction grating by how many slits there are in a certain distance. Because remember how we mentioned earlier, the diffraction grating is like Young's double slit, except there's many, 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 many slits. And you're going to get the same result, but just a much sharper and clearer interference pattern. So it's so much easier to get more accurate results that way. So when you can get the distance between the slits, your diffraction grating, so how many slits per meter or centimeter, 1 over that. So keep that in mind, and we'll use that in a little bit when we do our calculations. Okay, so our possessed red line is still following us. There we go. And so this equation here, as I mentioned, any diffraction calculation, go for it, use it to your heart's content. This guy can only be used when theta is less than 10 degrees. So this guy is going to be helpful in some cases, but not as helpful in others. So just keep that in mind. This one is going to be the most useful of the two. And of course, where can you find these? Data book. And to get your angle, so to get theta, you're going to use trig. So remember the triangle that I drew on our previous diagram? Well, here you have your length. That's supposed to be an L. And then here we have your value of x. So the distance between those, the bright spot that you are investigating. And you're going to get your theta. So what that means, ladies and gentlemen, and notice this dotted line, or this line I am currently dotting, that line, ladies and gentlemen, that is exactly where the light is going to be traveling. That's that line of constructive interference. Okay? So in order to get theta, ladies and gentlemen, you're going to use tan. So tan of theta, well, opposite of or adjacent, is x over your length. So that is how you're going to get your theta. Sounds good? We're happy? Cool. All right. So let's look at a few calculations, ladies and gentlemen, as we're being followed by this red line here. If this light wave seems to want to hang out with us. There we go. All right. So light falls on a pair of slits this far apart. Well, ladies and gentlemen, that is our value of D. And the maxima, so remember the maxima, those are the bright slits, those are the bright lines, okay? They're this far apart. Okay? And the screen is that far away. So there's your L. What is the wavelength of the light? Okay, so we're trying to find lambda. Now remember how I said earlier that if you aren't given n, assume it's 1? Well, why is this going to work in the scenario? Well, I said the distance between the maxima are this far apart. Well, here is n equals 0. Let's say this is n equals 1, and this is n equals 2. Well, I said the distance between the maxima. Well, the distance between 0 and 1 is going to be that value of x. The distance between 1 and 2 is going to be that value of x. Whereas if we're going to go make n equal 2, we're going to have to double that x value. So that's why we're going to be using n equals 1. So let's look at what we have here. We have these guys. Well, oh, hey, look. Well, that would be super easy. We just plonk it into that super awesome equation, our lambda equals dx divided by nl. No, we can't do that. Why can't we do that? We need to see if theta is less than 10. So the nice thing is we have to find theta anyway. So it doesn't really matter what equation we're going to be using in the end because we need theta for that second equation and we need theta to use the other one. So we may as well find theta. It's not really an extra step. So I'm going to draw my triangle. That's supposed to be a right angle triangle. So I've got my length, which is my 1.28 times 10 to the... Did I write my... No, I'm writing my number in the wrong spot. I did this again, the exact same thing when I made the video the first time. Because this is take 2, guys. I seriously had the whole video done. And then the computer killed it. So this is take 2 for me. So L is 0.55, and this is your x, which is your 1.15 times 10 to the negative 1. So what we're going to do is we're going to use our tan theta, which is equal to our x over L, which means we're going to go tan negative 1 of x over L is going to give us theta. So theta is equal to tan of negative 1. And your x, ladies and gentlemen, 1.15 times 10 to the negative 1. And then we're going to divide that by 0.55. Make sure you put it in your calculator. Make sure you're in degrees. Otherwise, you're going to have a rad time. Okay. So you're going to get your theta of 11.8098 degrees. Well, guess what? That, ladies and gentlemen, is greater than 10 degrees. So therefore, you cannot use your lambda is going to be equal to your dx over nl. So you are absolutely 100% going to must use our other equation. So we're going to pull out our other equation from our data booklet. So your lambda is equal to d sine theta divided by n. Well, I already found sine theta, so I'm just going to use that value. And d is this guy here, so 1.28 times 10 to the power of -5. Multiply that by sine of 11.8 ... using all numbers in your calculator, please. And n is 1, so divide that by 1, or just don't divide it by 1 because it's going to be the same thing. Yeah, don't divide by 1 in your calculator. You do not have to do that. So we're going to wind up with lambda as, with your sig digs and rounding, etc., 2.62 times 10 to the power of -6 meters. Alrighty-o, ladies and gentlemen, I've got a quick challenge for you guys while we're at it. What color is the light? Figure it out. Let me know when you find out. All right. And our random light wave is still following us. Okay, it really, really wants to hang out. Oh, yeah. Okay. So calculate the angle of diffraction of the second order. Okay, so we want theta of the second order maximum. All right, so that means our n is 2. Produced by directly shining monochromatic light with that wavelength. Okay, another challenge. What color is that laser beam? Through a diffraction grating with that many lines per meter. Well, notice our units, lines per meter. So our lines per meter, ladies and gentlemen, remember that we can use this guy. Okay, so with that, we are then going to wind up with our actual value of D, which is, there we go. Okay, so don't forget that step there if you have been given lines per meter or lines per centimeter or something like that. Okay, so ladies and gentlemen, well, I'm trying to find my theta, and I have n, lambda, and d, so I'm just going to use this equation. Okay, so I'm going to use this guy. I'm going to rearrange it so then that way I can get my sine theta. I'm going to multiply both signs by n over d. Okay, so those all cancel, and I'm going to wind up with sine theta, which is going to be the lovely value of n times my lambda divided by d. Okay, so what I personally would do is in my calculator, I'd find sine theta first. So 2, multiply that by my lambda of my 4.3 times 10 to the -7. This is going to reduce your calculator errors in some serious ways. And then you're going to divide that value by your 5 times 10 to the -6. And once you plunk that into your calculators, you're going to wind up with 0.172. That's a 7. Okay. Now, once you have this, then you can go into your calculator and do your sine -1 of that answer. Okay. Which would then give you the lovely theta, once you've done your sig digs and your rounding, of 9.90 degrees. Go Baines? Go Baines. So once again, don't forget that calculator in degrees, or you're going to have a rad time. And we don't have a rad time in physics. We have fun. It's not a rad time. You guys miss me, really. Okay, a couple theory questions, and then we're going to call it a day. Get rid of this. Now, with these two questions, we're going to use your favorite directly proportionate and inversely proportionate scenarios. Okay, so they're not too painful, but we're going to, oops, there we go. All right, so if the distance between the slits is increased and the diffraction experiment is similar to Young's experiment, how would the angle of diffraction change? Okay, so in the videos that I've given you guys on Young's double-slit experiments, there's 3 of them. It'll be really good for you to watch when we're done this. On one of the 2 first ones, I think it's either Young's double-slit part 1 or Young's double-slit part 2. I can't remember which one. Maybe even the 3rd one. I don't remember. It's been a few days since I screened all those videos for you. They go through this question very similar like this, and they do a wonderful job of it. And they even take those wavelengths and they move them on top of each other. They've got way better tech than I do, so they can really show what happens at those angles. So watch that video, have a look at that. Okay, we're going to do this mathematically. Okay, so we have the distance between the slits is going to be increased. Okay, and well, we then we're trying to find out what happens with theta. Okay, well, let's look at our equation with theta. Sine of theta is equal to, oopsie, I wrote stuff down weird. Let's try this again. Getting ahead of myself. Okay, we're going to take our equation. Your lambda is equal to d sine theta over m. Well, what we want to do here is we want to get our d and our sine away from each other. We want to get them on opposite sides of that equal sign so we can really see what happens when we increase one and decrease the other. So I'm going to rearrange this. So that way I can get, by the same way I did up earlier, I'm going to multiply both sides by n over d. And I'm going to wind up with my sine of theta is going to equal lambda n over d. Now, because I want to see how d is going to affect theta, I'm going to just make everything else 1 and stick a proportionate sign in there so we can see how changing one would change the other. So sine of theta is going to be proportionate to 1 over d. Okay, because I replaced both of these guys with 1s. Okay, so that means sine of theta is inversely proportionate to the distance. Well, put into your calculator sine of 0, you get 0. And then if you put, and as you increase theta, you increase sine of theta. Okay, so that isn't going to change our concern with that number there. But if we increase d, that means theta is going to decrease. If we decrease d, sine of theta is going to increase, so therefore theta is going to increase. Okay, so the question asks, if we are going to increase d, what's going to happen to theta? Well, theta is going to decrease. Okay, so ladies and gentlemen, there's that one. Okay, let's look at our next one. So a blue laser was initially used in Young's double-slit experiment. How would the distance between the bright bands, so we're looking at, we're not looking at D, we're looking at X. Okay. How would the distance between the bright bands change if a red laser was used? Okay, this is where you're going to want to pull out your beautiful EMR spectrum pages. So pull that out, and I want you to have a look at see where your blue and where your red is. Well, red has a lower frequency and a larger wavelength than blue. Blue has a higher frequency and more energy. So we're trying to figure out, well, what happens to X, and what are we doing with our wavelength? Well, if we use a blue laser, it's going to have a shorter wavelength, and if we use red, it's going to have a larger wavelength. So we're increasing our wavelength. Now, let's think about this for a moment. Blue lasers have more energy than red lasers. So why on Earth in Star Wars and Star Trek and all of the other sci-fi shows do they use red lasers when they have the least amount of energy? I know, right? They should absolutely all be using blue lasers. Anyway, sorry, I couldn't help it. So, as just an aside, an extra for when this is done, I will completely debunk a whole piece of the most recent Mission Impossible for you because physics. You won't be surprised at how often I get told to be quiet while watching action movies because I just sit there like, yeah, no, breaks laws of physics, doesn't make sense. Yeah. So my husband's like, just watch the movie. It's fun to debunk them. Anyway, I'll debunk Mission Impossible for you after. Okay. So let's look at our equation again. So we have in this case, let's use our lambda is equal to xd over NL. Well, in this case, ladies and gentlemen, we're trying to focus on x here and our lambda. Everything else we're going to make 1. And then we're going to throw in our proportionate sign. Well, look at this. Lambda is directly proportionate to x. Because lambda and x are directly proportionate. Back again, this is take 3 of the video. So ladies and gentlemen, this is like the 3rd time in 2 days I've had Screencastify crash on me. So please forgive the absolute disaster that this video is format-wise. I'm just glad we at least have the internet to muddle our way through this. So let's finish question 4, and then I will debunk Mission Impossible, as promised, and then you guys can finally be done with this choppy mess of a video. All right, so ladies and gentlemen, as we mentioned before the video chopped off, we've got a blue laser and we're replacing it with a red laser. So what would happen with lambda is our lambda is going to increase. Okay. And we're trying to see what would happen to the value of our x. So, which is our distance between the bright bands. So we're going to use our equation, lambda equals xd over nl. And, well, ladies and gentlemen, what we want to do is we need to get our x and lambda all nicely sorted. And, well, guess what, ladies and gentlemen? They kind of already are. We can just replace all of these with 1s. Okay, so our lambda is going to be directly proportionate, replace all these guys with 1s, to x. Awesome, hey? So because they're directly proportionate, well, if we're going to increase lambda, then we are going to increase x. Okay, so ladies and gentlemen, we have finally finished this video as far as the science goes. Got some practice problems here that you guys can work on. Those ones there, give some of those a try. Give some of these a try. They're all in notes. All right. If you are done listening to me, Natter, you're welcome to stop the video now. If you really want to see the math behind why Mission Impossible Fallout is complete garbage according to the laws of physics, stay tuned. So what I did is you guys looked at, we're going to focus on those plutonium spheres that Tom Cruise is dancing around with, swinging around in a lovely, cheap, plastic-handled briefcase, and they're like throwing them at each other. And they're sliding across the ground and tackling them and hitting the chest with these 3 plutonium spheres. Well, when you look really carefully at them, they look exactly like what they are, hollow aluminum spheres. So I did the math. I calculated the approximate volume of the sphere using our equation. And I made the assumption that the radius of these is going to be about 5 inches, which turns out to, using I converted the units to 12.7 centimeters. So once you throw that in there, do the math, and you're going to wind up with a volume. Yeah, so about a little under 5,000 centimeters cubed. Well, I did a quick Google search to calculate the average density of plutonium. Well, the density ranges depending on the isotope, and it ranges from 16 to 19.86 grams per centimeters cubed. So I just took the average of those two numbers to give us kind of a middling value. So this is the number that I used in my calculations. Well, your density is equal to mass over volume. Mass is equal to density times your volume. So I took this number, multiplied it by this number, and I wound up with a mass for one of these spheres to be 86537 grams. Well, that's annoying, so I converted it to kilograms. So we have 86.537 kilograms per sphere. Well, there's 3 of them in this briefcase that Tom Cruise is toting around like a goof. So I multiplied that by 3, and we are going to get 259.6 kilograms. Well, to put this in perspective for those of you who like imperial, I converted that to pounds, and so all 3 spheres are 565.70 pounds. Yeah, these guys are flinging around like 565 pounds of plutonium like it's nothing. So guess what? They actually were using hollow aluminum spheres and didn't take a moment to do like some grade 8 math to even come up with some closely accurate physical properties of their prop. I mean, sure, use hollow aluminum spheres, but at least fill them with cement, make them look reasonable. Anyway, I hope I haven't crushed your soul by ruining Mission Impossible Fallout too badly. But I couldn't help it. I could not help it. So yeah, and I truly, actually like did the math on some scrap paper here. So I had it all ready to go for you guys. All right. So ladies and gentlemen, have a good day. I'm sorry about the technological disaster that this video is. No fires, injuries, or explosions. And now I can't exit. There. I will somehow eventually stop this video. Okay. Talk to you guys later. Bye.